Hello and welcome back. Today we're going to be looking at 2023 day 9. I might go back and do day 8 at some point, but um, I thought day 9 was really cool um, because the problem itself has some very interesting math behind it, which I'm excited to share with you. So let's dig into it. Um, let's see. So basically, flavor text, you get inputs where each row is a sequence of numbers. And then for each one of these rows, it says in order to solve it, you basically construct this sort of pyramid or table. And the way that you construct each row of the pyramid is each cell is the difference of the upper right element and the upper left element. So like if our first sequence is 0, 3, 6, 9, 12, 15, we do 3 minus 0 is 3, 6 minus 3 is 3, 9 minus 6 is 3, etc., etc. And you basically keep performing this function until the row consists entirely of zeros. And then once that is the case, you can add a 0 on the far right, and you can calculate these values to get the next value in the sequence. So this this problem is all about predicting the next value in each one of our numeric sequences in our input. This is one way that you can do it. So you calculate all these values. You might notice that this value that we care about is actually just the sum of the last kind of the last column in this table, I guess. So that's the test, and then once you have the next value in the sequences for all of them, you add them all together and you get some answer. Cool. Well, I solved this in a fairly basic way, just basically following the examples here. We can go through that real quick, and then we will dive into some crazy math. Okay, so we'll use ng for the simple solution. So we're just loading our input. For each one of these, we can eval. We get numbers, assign this to p. And then, for example, we can look at the first row of p. And then we'll use each prior minus, and we have to apply it. So each prior will take each element and subtract the element before it. You get this 0 on the far left, and that's because there's an overhang for each prior. And so we want our sequences to basically decrease in length by 1 each time that we run this. So we'll just drop the first elements, right? Now we can run this using a while loop, and we'll run it while there are any non-zeros in the rows that we're calculating. So this is 0 equals not, so 0 not equals, and as long as anything in the row is not equal to 0, we'll keep going. And instead of a reduction here, we'll do a scan, so we get all the intermediary rows. So this table looks pretty much exactly like this one. All that we need to do is for each one of these, we just reverse all the rows, and then we can take the first element for each one, and then we can add them all together to get 18, which is the next value for this sequence here. This can be a train, and it can be run for each row of p, and then if we add them all together, we get 114, which is the answer for the test input for part 1. By the way, part 2 basically asks us to do the same thing, but on the other side. This is equivalent to just reversing your initial input and running the calculations and doing the same thing, but on the left side. So if we want to do that, we can just do for each reverse on our inputs, and we get the value 2, which is the answer for the test input for part 2, right? Okay, so that is sort of basically the way that I solved it, not too hard to do, pretty easy with like each prior and the nice scans that NGNK has, right? Okay, so then I was hanging out on the APL Discord, and once again, Rock 1507 pointed out that we can once again use matrix inverses, and I was like, how does that work? Now, I am not I'm not a mathematician, not by a long shot, and I didn't really know about a lot of this stuff beforehand. So, just I'm it. This wasn't necessarily my solution. I'm just bringing wisdom down from the mountain here. Okay, so it turns out what we're actually doing is something called divided differences, and I guess this was originally something that Newton did, and it was used in Charles Babbage's difference engine, which, name, I guess it makes sense. A recursive division process. And we can sort of see here that for each one of these elements, so like yk plus 1, we're subtracting, yk. It turns out that we are doing finite differences, and finite differences or divided differences in general can be used to calculate the coefficients of an interpolation polynomial. Now, what does that mean? Well, basically, the idea with predicting the next value in these sequences is, let's say that we have some polynomial, right? Which is basically just like, you have like x squared, x, and then some constant. You can have x cubed, x to the fourth, whatever. Then you have some coefficients associated with it. It's like a, b, c, whatever. And let's imagine that the rows in our inputs are actually the outputs of this function at like different values for x. So we might start with like x0, x1, x2, etc. You can sort of think of like plotting these on a graph, with x values starting at 0 and monotonically increasing. And we are trying to come up with a polynomial that fits all of those points. And then once we have that formula, we can extrapolate the next point. Now, this finite differences thing that we're doing is like equivalent to finding the derivative, apparently. I haven't taken a math class in a long time, okay? And I think, based on what I've been looking at, I think the fact that this converges to 0, or is basically stated to converge to a row full of zeros for every row in our input, means that there is an exact polynomial solution for all the rows in our input, right? So yeah. So the idea is basically we are trying to find the coefficients of a polynomial that fit all of the points for each row in our input. And then once we figure that out, we can evaluate the next term in the sequence to get the value that we want for each sequence, and then we just add all those together. So yeah, some light reading for you if you're interested in this stuff. There was a useful YouTube video that someone linked from someone called the Mathologer, which I found pretty helpful. So I'll link that in the description maybe. But okay, now that we know what we're doing, we're basically trying to interpolate this polynomial. Turns out that we can do this with this thing called a Vandermonde matrix. Okay, so the Vandermonde matrix is basically, you can generate it for any size that you want, but it's going to be a square matrix. And if you think about the sequence from like starting at 0, so like 0, 1, 2, 3, etc. Each each cell in this matrix is going to be the index of the row to the power of the column. So on the leftmost column, we have everything to the 0th power, so you just get like a bunch of ones. And then you get everything to the first power, so it'll just be the numbers, and then squared, cubed, etc., right? And it turns out that this can be used to find polynomial coefficients. So if we have our values that if we have our values here that we know are the result of like applying the polynomial at like 0, 1, etc. Turns out that we can find the inverse of the Vandermonde matrix and then do a multiplication against this to find all of our polynomial coefficients. And then once we have our polynomial coefficients, we can evaluate the next term in the sequence. So yeah. Yeah, it's pretty wild. This is some new math that I didn't know about, so that's pretty cool. Like I said, I'll link more stuff in the description, but let's see how we can actually do this. So we are in APL because APL allows you to pretty easily take the inverse of a matrix. So we can start with the test input. So we have this. For each one of these, we'll execute to get numbers. We will mix it to turn it into a matrix, and then we will transpose it. This will make it slightly easier to work with in the future. So we'll assign this to P, and then it's also going to be helpful to have the length of this matrix. So we'll assign this to like R. We'll use this in a bit. Okay, so for P, basically each column now represents, oh, by the way, I should have mentioned that it turns out that each one of the sequences in our input has the same length, so that they fit into a matrix nicely. So each column in P now represents a sequence in our input. We can get the first one by doing a right tack or left tack reduce. And let's say that we're going to run some function on this. So first, we want to generate the Vandermonde matrix of the correct size. We have R, which is the length of any row in our inputs, and we can do iota R to get sequence. We want to be in IO0, by the way. This is going to make things a lot easier. So let's try this again. We get the sequence starting at 0. And then we can generate the Vandermonde matrix by doing an outer product power or exponential. And that gives us this. So like I was saying, each cell here is going to be equal to the value of the let's see. So the first row is going to be everything to the power of 0. Second row is going to be everything to the power of 1. Third row will be everything squared, and then everything cubed, everything to the 4th power, everything to the 5th power, right? Now, let's take the inverse. So we can take the inverse with domino, which, as I stated in the, the day 4 solution, never used this in an AOC problem. I wanted to for a long time, and it's crazy that this is now the second time in a year where we're able to use it. So let's find the inverse. You will note that we are no longer working with pure integer values. So from here on out, there may be some precision issues because we're basically approximating things with floating point numbers. Okay, so we have the inverse, and now we can take the first row of our input, and we can do a matrix multiplication, right? So if we look here, basically the way that this formula works is the Vandermonde matrix times the coefficients of the polynomial equals the evaluations of that polynomial at various values of x. So if we want to find the coefficients, we can take the inverse of this and then left-hand multiply it by our sequence in order to get the coefficients alone. And we get this. These values are incredibly close to 0, by the way, so we can sort of round these to the nearest number by adding half and flooring. Okay, so this is the coefficients for the polynomial for our first sequence and our input, right? Which sort of makes sense. The first row in our input is just adding 3 each time. And the way to read the coefficients is there are 0 x to the 0ths. There's 3 times x to the first power, and then 0 x squared, 0 x cubed, etc. So basically this just boils down to 3x. And if we think of our sequence as like, our polynomial f evaluated at 0, 3 times 0 is 0, 3 times 1 is 3, 3 times 2 is 6, 3 times 9, or 3 times 3 is 9, etc. Right? So if we want to evaluate the next term of the if we want to evaluate any term of the polynomial, we can basically take iota r and then just take some number to the power of each one of those numbers. And we can do another matrix multiply here. So we're just multiplying, we're multiplying x, we're multiplying each. So like if we take x equals 1, right? We're going to take x to the 0th, x to the first, x squared, x cubed, whatever. And then we're going to multiply each one of those values times all of the coefficients, and then we're going to add everything together. And so now we're able to, if we want the 0th term, if we want the first term, if we want the second term, whatever. And the term that we really want is r, which gives us 18. So, which is the answer for this sequence in our test input. And if you want to get super tricky, this is basically equal to reversing and then doing a base decode. So what base decode does, think about like if I do 10 decodes, 1, 2, 3, I get 123, right? And what this is doing is it's taking the left side and it's saying, okay, whatever you have on the left side to the 0th power, to the first power, to the second power, times all these, and then summing them up, which is what we were doing anyway. So, yeah. Now, here comes the cool part. We can do this whole thing. So if we look at like the shape of our input and we look at the shape of this Vandermonde matrix that we're generating, we see that the shapes, the first element of the shape of our input and the last element of this Vandermonde matrix line up. So we can just do matrix multiplication on the whole thing. And hang on. Oh yeah, we can't reverse the rows. We want to reverse the matrix itself. And this is enough to evaluate all of the next terms in the polynomials, and we get our part 1 answer for the input, 114, right? And if we want to do this for part 2, we just, again, reverse all the rows in the matrix. And we get 2, which is the answer for our part 2 for the test input. So, if we want to run this on the actual input, here's what it looks like. So we set index origin 0, we parse our inputs, we have this evaluation function that takes the inverse of the Vandermonde matrix, does matrix multiplication and the base decode, and then adds everything up. Except that if we try and run this, we get a domain error when taking the inverse of the Vandermonde matrix. And the reason is that when we try and take the inverse, we run into overflows. So by default, Dialog will use 64-bit floating point numbers. However, you can optionally ask it to use 128-bit floating point numbers. So this FR is for floating point representation, I think. And if you tell it to use 128-bit floats, now you can run it. And you get 2005, 35, 2194, which is the answer for part 1. And again, if we just reverse the rows of the matrix, we get the part 2 answer, which is 1077. And let's see, if we load compx from dfins, and we did like compx fp, we can see that it's like reasonably fast. So this takes 1.5 milliseconds to do. It's probably not the most efficient, but yeah, I thought this was really cool, and we got to use the matrix inverse function again, the old domino, which is super awesome. So it's this initially seems like a very simple problem, but there's some cool math behind it, and I think that there's a really cool solution here in APL. So yeah, hopefully you enjoyed. Probably gonna record some more 2023 videos, so stay tuned. Thanks for watching.